Good
Let's start
morning.
the session. Technical session will be from Eminent speaker, Dr. Surendra.
Hi, Bera ma'am.
Hello.
Hi,
Good
sir.
morning.
Good morning. Good morning. Good morning.
Okay, let me continue now.
Should I start?
Today's first technical session will be from eminent speaker Dr. Surendranath Somala. Dr. Surendranath Somala is a senior scientist in physics, a pinnacle personality for Aliburton Service UK. He is currently working as assistant professor in Department of Civil Engineering at IIT Hyderabad, India. He is also visiting associate at Indian University Center for Astronomy and Astrophysics, Pune. Sir will be delivering lecture on seismic fragility and earthquake loss assessment. And I request Professor Antelina Person to chair the session. Over to you, ma'am.
Thank you. Thanks for introducing Dr. Surendra Somala. And well, I think we can start right now, and I give the floor to him. Thank you. Please.
Okay.
We cannot see the slides.
হ্যাঁ হ্যাঁ হয়েছে আমি শুধু সাজে মেসেজ পাঠাইছি ঠিক হয়েছে থ্যাংক ইউ হ্যাঁ হ্যাঁ আমি শুধু সাজে মেসেজ পাঠাইছি ঠিক হয়েছে থ্যাংক ইউ
Okay, is my presentation visible now?
Yes, sir, it's visible.
So, good morning, everyone. Welcome to the second day of ASSHEE meeting. So, I'm Surendranath Somala, faculty at IIT Hyderabad. I'm going to talk about seismic fragility and earthquake loss.
Yes, sir, it's visible. Yes, sir, it's visible.
I think some of you need to mute yourself. All those who are not. So how does this fragility work? What is all this fragility about, and what is the fragility of structure? How does it help in computation of risk? Risk is basically loss assessment. What sort of losses do we see in the scenario event of an earthquake, or if we can pre-estimate what is going to happen beforehand, we can at least plan some mitigation measures. So most often you see people talking about post-earthquake stuff, but this preparedness is all about the ability to compute a priori what sort of risk you're going to have. And the template for that is something like this. Of course, fragility forms a basis for it. It's not the end goal. Risk is somewhere over here. So what you really know is we have some buildings, and we subject them to say excitation. The excitation need not be same at all the supports. For buildings, of course, because the span is small enough, typically they are equal in size. But where do we get this earthquake data from? The earthquake data is typically scaled to the design response spectrum within the time period of interest to us. And it has to do with the fundamental time period of the structure that we call as T1. And typically we do the matching in between, say, 0.2 T1 to 1.5 T1. That's what the building codes specify. So after scaling the ground motion to the design spectrum, which is shown in red in the bottom left plot here, all these blue curves are various earthquake data, and that is applied to the structure from both directions. We are interested in bidirectional response, mostly the horizontal components. Vertical component typically contributes to the uplift. So as long as we are not so much focused on uplift, we subject them to the horizontal components and compute these measures called inter-story drift. And that is done using incremental dynamic analysis. In this case, people sometimes use pushover and other stuff as well. But we typically resort to incremental dynamic analysis. So what is incremental dynamic analysis? So you have your earthquake data here, you scale it by small factors and then keep subjecting that to the earthquake, and each of them give you one point on this curve. And various curves here represent various earthquakes. So once you have the IDA curves, from that it's possible to derive fragility. I have a better slide later how that happens from IDA to fragility. But it's the fragility that forms the basis in risk assessment, risk-targeted ground motion, and anything that has to do with the risk. So performance-based earthquake design is all about, see, lots of decision variable. The decision variable has to do with the risk. But before that, you have these design ground motion, which are obtained by either scaling or response spectra matching, and so on. So how does fragility really look like? Fragility is basically a log normal distribution in simple sense. Is this the only distribution there is? There can be multiple such cases, but it has been widely used in literature. Most failure thinks this is what you use, log normal. So this is phi, capital Phi is the standard normal, and your random variable here is the spectral displacement, and that's expressed in terms of logarithm of spectral displacement. What you have below is with a bar here that has to do with the median value, and the subscript ds has to do with the damage state. So what are the damage states? I'm going to talk about the next slide, but beta here is the dispersion of the standard deviation of this thing. So this is the probability that you experience a certain damage state given that the spectral the spectral displacement or the earthquake demand to be of certain amount. So fragility curve, as I said, the shape, the equation was shown on the previous slide, and the shape of it typically looks like this, log normal sigmoid thing, where most of it is happening over here. This is 0 probability at the bottom left, and top right is the 1% probability, your x-axis and y-axis for the fragility curve, or the intensity measures and the damage measures. So intensity measure here can be peak ground velocity, peak ground acceleration, but nowadays typically you see in design codes spectral acceleration at the fundamental time period, SA of T1 most often, or in some sort of average sense. Of course, intensity can also be your MMI, modified Mercalli scale intensity, or EMS scale, or things like that. But when we have good earthquake data, you can actually compute even the spectral acceleration at the fundamental time period of structure. That correlates very well with the damage. What you see on the y-axis here is the damage measure. Damage typically for the structural components, like the moment resisting frames, the entire integrity of the structure is coming from the beam columns and how they're connected. So for that, the damage measure is typically the inter-story drift rate. Inter-story drift ratio, you'll see in some cases. But peak floor acceleration is also important when you're talking about non-structural components as a damage measure. But this is how the equation looks like for fragility, and this is how the shape looks like. But is there only going to be one curve? No, because you're going to have multiple curves, because you're going to define multiple damage states. DS here is the damage state. Damage states are typically defined as, in most codal provisions, FEMA in this case, this is taken from Hayes' manual. Hayes is Hazard United States. It's the advanced version now for Hayes is FEMA P65. So what you're seeing on the y-axis here, probability that the damage state, a particular damage variable exceeds certain amount that you define as in codal provisions, 0.2% drift, 1% drift, 0.5%, or 2%. Given that you know what the spectral displacement is. So displacement-based design, you keep seeing spectral displacement instead of spectral acceleration as a intensity measure. And what are these multiple scales here? Slight. It's like your traffic signal design. The green has to do with everything is safe, nothing to worry about. You can immediately preoccupy the building after the earthquake. You readily occupy the building. Moderate, you may end up seeing small cracks, but they're repairable. Extensive, there needs to be some repair done before occupying, and collapses obviously you can't really take it. But then what are these limit states, and are they dependent on structure? That we are going to see in a bit. But so although you see the curves in the previous slide, but it's the hashed region here that belongs to each damage state. So slight damage state has to do with anything between this first curve and the second curve. Then moderate damage has to do with the second region, and third extensive, and finally complete. Again, this is taken from Hayes' manual showing for various kind of shaking what sort of damage you experience. Remember, all these are your log normal curves, except that each of them are defined for certain damage state. And damage state can be in terms of interstory drifts. So what sort of classification is there for fragility curves? What I just described here is mostly the analytical part, where you do rigorous structural analysis. You subject your structure to incremental dynamic analysis of ground motion that you have selected or scaled from recorded earthquakes. Some codal provisions permit even simulated earthquakes. And from the IDA curves, you fit your log normal to IDA curve at the damage state that you're interested in and get your analytical ones. But empirical ones are based on post-earthquake survey. So let's say some field survey has been done after an earthquake, and there are lots of these photos that shows various kinds of tracking, and based on that, if you define certain fragility curve, having known the intensity measure that's experienced by that location, you may call it as empirical fragility curve. And there are also judgment based, like in GMPEs, you see expert opinion. So experts in earthquake engineering, particularly in the field of earthquake engineering, you take their experience and fill up all the fragility curves. Hybrid is a combination of them, but now in FEMA P65, you see most of these fragility curves already defined for all kinds of structures as well as all kinds of non-structural components, both in terms of the dispersion as well as the median value. Median is the 50 percentile value. So how do we derive fragility from incremental dynamic analysis or the IDA curves? So the figure you see on the top right is the IDA plot, where x-axis is the residual interstory drift. You can also have peak interstory drift sometimes. With respect to this intensity measure, as I said, it's the spectral acceleration at the fundamental time period T1 for 5% damping expressed in terms of G. So this is about 2G, 1G level is over here, but this is horizontal, so there is no uplift. If it were vertical, after 1G, you will see uplift happening. So again, the traffic light signal kind of design, going red to green to red, where green is like everything is fine versus red is almost complete collapse. So this is actually real work done, published in ASSHEE conference proceedings for Delhi. We studied some reinforced concrete buildings, and the limit states for them, the damage states are defined in terms of 0.2% residual interstory drift, 0.5%, 1%, and 2% for each of the 4 damage states: slight, moderate, extensive, and collapse. So if I fit a probability distribution over here for this collapse limit state, starting from this lowest end to the highest end, that will give me this red curve that you see over here. Similarly, if I fit a probability distribution for the extent this black curves are spread over this dotted green line, that will give me this green curve. Of course, there are some subtle things to be addressed that sometimes you will see crossing over of these things. So just a regular curve fit may not work well. So there are also things defined in terms of probabilities. What's the like? If you go into the probability aspect, then you may at least make sure that these things don't really cross each other. But these are various curves for various earthquakes subjected to basically the same building, and we are measuring here the residual interstory drift as you scale up the ground motion slowly. So what are the building types that FEMA P65 talks about? So FEMA really talks about wooden buildings as well. Wooden buildings are widely seen in California, where you have earthquakes for breakfast, dinner, and lunch. There are also steel moment resisting frames. Also, in each case, you have low-rise, mid-rise, high-rise, three categories based on which you have different median and dispersion for the fragility curves. So you have steel moment resisting frames, then you can have bracings and things like that. Then also, in terms of concrete, you have various categories: just a bare frame versus with shear walls and so on with infills, or precast concretes, and there are also mobile homes. So typical median value for low rise is mostly 2. In most of the cases, you see 2 stories called a low rise thing. Of course, anything from 1 to 3 is low rise, and anything with 5 stories is mid rise, and say around 8 plus with median value of 13 is typically a high rise. So their heights are also given here. Typically, a human is 6 feet, so this is like 4 times a human being, and so on. But in Indian context, we don't see this type of buildings mostly. This is a work done by us for Indo-Gangetic Plain based on some building inventory information collected by Roorkee team headed by Professor Arya and others. So the building classes in Indian context are somewhat different. We talk about adobe mud mortar with temporary roof, or adobe lime with cement mortar, or mud mortar bricks with temporary roof. But broadly, all these are classified based on 3 things. One is what sort of flooring there is, what sort of material is used for the wall, and what sort of roofing is there. So whether they really used bricks or adobe, whether they used RC wall, and again, there can be low rise versus medium rise. We don't see high rise in Indo-Gangetic Plain mostly. So, or basically they're only a handful. So that's about the structural part, the framing, the entire thing that's resisting. Why are we interested in non-structural aspect? Let's say if you have a hospital, the hospital may withstand the earthquake if you design the structure very well as per the codal provisions. But then the non-structural components, there is a real YouTube video, if you can see, the shake table test that was done at E-Defense, the NIT Japan's shake table, the largest once upon a time. So they have constructed a hospital building model, and inside that they put lots of beds, and they subjected to earthquake shaking. The building itself does not experience much, but then the beds inside, the hospital beds, they move drastically. So actually the non-structural components, most of the majority of them are acceleration sensitive. They are not drift sensitive. So drift is like the displacement, and acceleration is in layman's terms, double derivative of it with respect to time. So peak floor acceleration is also important when you're talking about structures that are in different risk category. So acceleration sensitive regime. But there are of course certain small number of non-structural components that are also drift sensitive. So in such cases, you may end up doing facility for both acceleration based as well as drift based. So structural components are drift sensitive. So most facility curves you see for structural components are drift based, whereas for non-structural components it's acceleration sensitive. Then what are this high code, low code, moderate code, pre-code? So building codes are also knowledge that we develop after each earthquake, and then we document them in such a way so that we, in the future, when you construct something, you can follow those codal provisions, or even if you want to retrofit the structure, you can follow those codal provisions. So pre-code is when you hardly had any code, or low code is when the codal provisions have just begun. I'm not going into the exact details of the years here, but moderate code is after some strong earthquakes, initial ones that you're seeing. San Fernando, probably, and so on. High code is probably after the Northridge, Kobe, and so on. So, as I said, the damage state is dependent on the kind of structure. So, wooden structures have different damage states versus concrete steel. But concrete steel, depending on low rise, this L here that you see is for the low rise, and so slight damage is at 0.4%. if your drift ratio is, if you have 2 stories, top and bottom, there's the difference between the top story lateral sway moment to the bottom story divided by the height of the story. So that is what we term as the drift ratio in coastal provisions. And if that exceeds 0.4% for the wooden structures, we call it as slight damage fragility. And this is 1.2%. 1.2% is moderate, extensive is 0.4%, and complete is about 10%. So similarly, it's prescribed for other structures, other types of structures as well, based on also the codal, when it was designed, and the year of built of the structure is also important. Unfortunately, in our census data for India, we have population and built inventory, but the age of the structure, and approximately the year that it was built is not that very well available. So typically slight damage varies in this regime, 0.3, 0.4, 0.5, and so on. Moderate is much higher than that, and extensive is even more higher. But this is where you start seeing cracks, and without repair you can't enter the structure, and this is basically complete collapse. You need to disregard the structure, start building a new one. It's not cost effective even to retrofit if complete damage happens. Complete damage, as I said, basically means the drift has exceeded more than 10% in wooden buildings, even though you have designed it for the highest available codal provisions as of date. And this is all taken from PIMA P65. Now, to do all this analysis, we need a spectrum. One is you can use the design spectrum given in the codal provisions. For example, for Indian context, it's the IS code, or you develop your own site-specific local thing. And this is a small advertisement for one of the works that we have done in terms of response spectrum development for Indo-Gangetic plains using machine learning principles. Basically, this is neural network. Of course, we are not the first to do. There are some others that you would see, but the choice of variables here have to do with MW has to do with the source effect, and some of these have to do with the path effect, and this has to do with the site effect. And what you populate here towards the right is the response spectra, where PGA is the 0th time period asymptotic of the response spectrum. And these are pseudo-spectral acceleration or the spectral acceleration at various time periods. In between, you have some hidden layers for this training of the neural network. And we found that our curves very well follow the real data. Although we have kept away some amount of data for validation and other purposes as well. This is published in Soil and Certification, and you can refer to it. But the reason for mentioning this is you may need sometimes site-specific design spectra for scaling of ground motion. Remember, in the very first slide, I told you, whatever earthquake data you have, you can't just subject your building to that. You need to first scale them or spectral match to the design spectrum, target spectrum, or to the site-specific spectrum, or risk-targeted spectrum. You will also see risk-targeted spectrum. And where do you download this earthquake data? So Strong Motion Center, also popularly called Cosmos, this website makes available data from all these places. And in the early days, during Chamoli, Uttakashi, India also used to share some of the earthquake data, and you would see those data here. But I think afterwards, Indian earthquake data is predominantly available at Tesmos. You have to check if the website is up or running now. But this is this Center for Engineering Strong Motion Data. It's a collaboration between USGS, California Geological Survey, NSS, and so on. Not only you see here the strong motion data, but the seismologists are broadly interested in these broadband velocity recordings. But for engineering applications, we typically rely on the strong motion data. Strong motion data from strong earthquakes, and preferably in the near field region. Those far field effects are also well studied. So the advantage of the Strong Motion Center is you see not only the strong motion data from sensors recorded on the ground, but there are also instrumented buildings. So there are bridges with sensors placed in systematic manner, hospitals in California and places like that were very well instrumented, and those also can be found over here. So if you take that earthquake data, then how do I get the data ready for doing the structural analysis of structures. So first thing is, how many do I need to choose? So recent codal provisions mostly talk about 7 to 11. There are also some codes you see maybe even 3 ground motion. 3 is too small a number. Of course, with 1 you cannot derive any fragility. There are no statistics existing for 1. So people, the bare minimum use 3, but 7 to 11 are typically used. By the way, the procedures, these steps are also important even for design perspective as well. For design of structures as well as for analysis to ensure whether it's collapsing or whether it's staying intact or whether retrofit is needed. For all these purposes, you need to subject the structure to lots of ground motion, and typically 7 to 11 in number. Earlier days or in the previous literature, you would see even 20 to 40 kind of ground motion. So as I said, you need to scale the ground motion to some spectrum. It could be your IS codal provision, or the targeted spectrum in recent times is MCE with a subscript R. The subscript R here is to denote risk targeted. So just like hazard is some certain amount of probability of exceedance in certain number of years, but there the exceedance is described in terms of intensity measure, like spectral acceleration or something like that. The targeted spectrum here, in this case, we describe the risk. What is the chance of collapse, of 1% probability of collapse in 50 years? So for a building owner, the hazard is not that important. For him, whether his structure collapses or not, that's of importance. So slowly, this probabilistic concepts of hazard have also crept into MCR. MC is maximum credible earthquake. That is risk targeted. The subscript R here has to do with the risk targeted, and basically it's a product of hazard times fragility. It's not without hazard. It also incorporates hazard into it. So MCR has to do with a combination of hazard and fragility. Then what sort of earthquake data should I consider? So let us say that there was Sikkim earthquake, and most of the earthquake data, there's only one really near field earthquake for the 2011 Sikkim earthquake. So that's about 50 kilometers Gangtok. But most of the stations are in the Garhwal kind of region, that of 900 kilometers. They are basically far field. They're of not much use or importance in estimating the structural response. What we really need are the near field strong motion accelegrams, which are extremely limited in the Indian context. Even if you scan the PESMOS database, firstly, most of the earthquakes there are less than 5 or so for the time period that they have. Also, there are 1 or 2, 6 and above. Most of them are far field earthquakes. The importance of near field also comes from the fact that there can be a pulse in the ground motion. Pulse typically manifests as a long period thing in the response spectrum, and it causes severe damage. Unlike earthquake, which is roughly broadband, is all encompassed with all kinds of frequencies. Pulse is dominant in one particular frequency, and if your structure has roughly similar frequency of the pulse, most likely your structure is going to experience collapses. So we talked about scaling, but what is the time period of regime that you need to scale for? So first thing is, of course, before doing anything, you need to know your structure, because T1 has to do with the structure. T1 is the fundamental time period or the first mode time period of your structure, and we're going to do that matching somewhere in this regime, 0.2 to 2, and in some places you will see 0.2 type T1 to 1.5 T1. That is the period regime or range where we want to make sure the spectrum matches very well. By the way, in addition to this MCER, there also you'll see nowadays conditional mean spectrum and some other advanced concepts that are for some other day, not for discussion now, because I'm trying to cover broad aspects here with general audience. Then scaling of ground motion. Which ground motion to consider? Because vertical is only one component, but horizontal you have 2 components. And recordings, in olden days, seismologists used to put the seismometers in such a way that you record radial and tangential directions. But your building may not necessarily be oriented along those directions. So sometimes there is a geometric mean of spectral acceleration considered, but these days in codal provisions you see maximum orientation is preferred. And the near fault, we are really talking about earthquakes that are exceeding 7 in magnitude. If you don't have data, you may have to simulate. So you need seismologists there, somebody who can simulate earthquakes, probably in the 3D context with all the topography and near field effects and so on. And less than 15 kilometers. These are the ones that are severely damaged. Or if you're talking about 6.5 to 7, we are talking about less than 10 kilometer kind of region. So this sort of data I couldn't find hardly any in Pesmos. You would hardly find even one for Indian context. That's strong motion. If they're available with Geological Society of India or somebody, please make it available so that structural engineers can make use of them and better things can be derived for Indian context. But most often you see that like even in GMP derivation, people say, oh, Himalayan tectonics is similar to some other tectonics somewhere, although we don't have recordings here, we are going to use similar GMP either from the similar tectonic regime. So there has been cases where people have used earthquake data from other regions with similar tectonics, but that's probably not that much recommended, particularly because the near field conditions, the site conditions, like the basin amplification, things like that can vary or change from location to location. So orientation of ground motion, as I said, the radial and tangential is what you find your ground motion in, but that's not what we want. And we need to rotate them into fault normal and fault parallel components, because only in one of these components you will see the pulse, especially the pulse-like ground motion for directivity or from super shear kind of principles. You will see them only in one of these components. So whenever you have near fault data, before applying to the structure, make sure you rotate it into FNFP, because the pulse dominantly manifests in only one of these two components. But in far field data, you can apply them in random orientation, doesn't matter. You don't have to do any rotation. That's what present polyns talk about. And spectral matching also, there is a small factor of safety of 1.1 here. So they match here to 1/10% of the target spectrum rather than the actual target spectrum. And make sure your drift falls within say 2 times the normal limit. This 2 also has some to do with the ratio of MC to dB and your ductility factor to response reduction factor and things like that. But this is the limit that we want to make sure your structure is within. So nomenclature of buildings, I think I've shown this briefly earlier also. One of the slides, we have Indian context and the Indo-Gangetic Basin. That's where most of the population is concentrated for India. Of course, we have also Northeast India with complex tectonic regime. It's the eastern syntaxis where Himalayan faults meet the Indo-Burmese. You have seen 1950 Republic Day earthquake and so on. So yeah, the building context in India, we see very little to do with the reinforced concrete frames, but we see a lot of them to do with brick wall, with temporary or permanent roofs or metal sheet roofs, so occasionally maybe concrete slabs and so on. So distribution of building types, which of these are dominant? By the way, as I said, I'm going to get into the case study where we have done this for the Indo-Gangetic Basin. So Adobe mud mortar were dominant by 29%, and then comes the BCM model building class and MMB and so on. So then we simulated 3 different earthquakes scenarios. So when we don't have real earthquake, all you can do is scenario earthquakes. Earlier, this used to be more important in the context of critical infrastructure like nuclear power plant and so on. But now, even for structural analysis, given that computation facilities have become really powerful, you can even do scenario earthquakes. And we tried out 3 different scenarios in the seismic gap region. Of course, this part has already been ruptured in 2015 Nepal earthquake, but there's a big seismic gap here, starting all the way from Kangra to Nepal Bihar, proposed the seismic gap 3 from Gurki, Khatri, and so on. Although they were Chamoli, Uttarkashi, they were not really, the seismic moment release in them was only like 6.5 to 6.8. But if you see some of the nature science papers, you see that there's a good potential for a large magnitude earthquake that can happen here. And even if it happens beyond the rupture region of 2015 Nepal, it may propagate in the other direction. That's when it is going to be more devastating for Indian context. So anyway, we proposed 3 different scenarios, 2 on the extreme, and one is the center. The extreme ones can be thought of a unilateral kind of propagation, and whereas the scenario 2 is roughly a bilateral propagation. You see these set of scenario earthquakes even in the shakeout context for San Andreas Fault in Southern California, So what we found in terms of damage ratio is, although the percentage of buildings wise AMM were dominant, it's the MMB model class building that has the highest damage. Because most of them have secondary damage levels also pretty high. All these two that are with low damage ratio are these really reinforced concrete buildings. Of course, we need to shift to reinforced concrete buildings eventually. Government is also in the scheme for housing for all and things like that. So if they are really proposing something, better not to go for this kind of building styles if possible, because they are only going to have higher damage rates. And damage probability is also computed for various damage types. Also, I need to mention here, we have used Selena for the risk computation in this case, but there are also many other software available. Nowadays, OpenQuake by Jump Portal, and they are probably more reliable. They make the best of all these available codes, all the freely available codes, if you want to say. So, what is interesting to note here for complete collapse, BTR or some of these building models, MMB, in terms of complete collapse, probable damage probability is very high. Whereas in terms of other probabilities, MMB is not necessarily that high. You see there are some other building classes that have higher damage probability when you're talking about moderate or some other. Then collapse rate and casualty for one particular building class, we have what is shown here in terms of pie charts as for the mud mortar building class. The damage ratio in terms of slight, of course, there's also N here, dark green, that has to do with no damage, slight, medium, moderate, extensive, and C for collapse. So we've considered, as I said, the central Indo-Gangetic basin. That's where we had some good recordings from the 2015 Nepal earthquake through a joint project between NGRA, IIT Hyderabad, and Japanese universities. So, of course, what you see here, red is more dangerous. Red is most of them are collapsing. So most of the collapse happens in this regime. But what's interesting, even this far away, the Himalayan faults are over here. But then even this far away, you're seeing very high probability of collapse damage state. That's probably because of local site conditions or other things that have been incorporated. It's not just the hazard that matters when you're trying to estimate the loss calculations. It's also the other things that really need to factor in. So in addition to damage, casualties are also shown, the deaths. Of course, these are shown in terms of time. The time of the day is also important. You've seen in the keynote lecture as well, as the time of the day is important. For example, if a movie theater, shopping mall collapses in the night, most likely there's nobody in there or office space. But as there's the popular saying goes, it's the earthquakes don't kill people, it's the buildings that do. So in that sense, so this is based on the time of the 2 a.m. versus 10 a.m. or evening time. What sort of casualties that you experience for various at a district level? There are some works done for Dehradun city and so on. We have managed to do it even at a district level for this entire state of Uttar Pradesh, where all the data like population is taken from census data and building classes. Then the relative importance of earthquake parameters. So the magnitude is undoubtedly the most important contributor. Basically, this is a sensitivity study for strike dip rate parameters, the focal earthquake parameters. Magnitude, if magnitude goes to the higher scale, the casualties drastically increase, or if it goes one level lower, of course, casualties decrease, but not by that much. Then the GMPs, we have chosen a couple of GMPs with logic tree weighted weighting, which are more suitable or particularly developed for that particular region. And GMP has equal weightage, whether you're going upwards or downwards. So second contender is the GMP. As I said, GMP is important in terms of that spectral matching. So Selena actually does it somewhat differently. They have this capacity curve and demand curve. Demand curve is from the earthquake itself, and capacity curve is specific to the particular structure. So where these two curves meet, that's the performance point. So based on the performance point, all the losses are computed. So magnitude is the highest contender. Then comes the GMP. Of course, source location also has significant prominence. But strike dip rate or focal depth, their importance is nominal or negligible when we compare with respect to these other parameters like source location. Of course, the strike and dip are also varied only marginally because those are what you find in the Himalayan context. Dip is only varied from 5 to 15. Typical dips you see are around 9 to 11 or so. Strike is already varied only within the typical strikes that you find in the Himalayan context. And focal depth also maybe 5 to 15 kilometers, because most of the Himalayan earthquakes of importance to Indian context are the shallow ones. So the take-home message here is after magnitude, if at all there is something more important, that's the GMP, and of course source location also plays an important role. Even if you don't know the strike dip rate, focal depth that well, it doesn't matter in terms of loss estimations or casualties. Of course, there's a lot of input that we have used in our work, and some of it has also been taken from there's Greek buildings, and this is from Italian context. So there are some building styles. As I said, GMP. In case of GMP, people take it from various other similar tectonic regimes. Similarly, here we took from other places or countries. We were not the first one, of course. There were also some other preliminary works done in the past with similar building classes, but only at a city level for Dehradun. So these are the capacity curve parameters, and these are the fragility curve parameters for various slight, moderate, extensive, and complete damage. So median value and then the dispersion. Median value and then dispersion for moderate case, extensive case, and collapse case. So in terms of capacity curve, I didn't really talk about it much, but what matters is two pairs of parameters. One is the DU-AU and DY-AY. So this is the Y subscript has to do with the yield condition, and U has to do with the ultimate condition. So the ratio of ultimate to yield is typically your ductility and so on. So these are for the Indian context taken from one of the works by Rupke. So replacement cost, again, this is taken from Lanka et al., but replacement cost, of course, these Adobe mud mortar, they collapse a lot, but the replacement cost is also lower. When reinforced concrete, they don't collapse much. The damage ratio is very low, but their replacement cost is also high. So that also needs to be understood. So I'm going kind of backwards. I've shown the results first and then showing the damage, the basics behind. So seismic damage is computed in olden days, the pre-2000 era, based on capacity spectrum method. Then there was also a modified version of it. But in the recent FEMA codes, 2005 and above, we see a displacement coefficient method where the spectral displacement is your displacement kind of a thing, and with some couple of modification factors, you get your performance point. So you first compute the effective time period of your structure based on the dy and ay, yield displacement and yield acceleration. And at that level, this is the elastic spectrum, spectral acceleration for the earthquake data that you have, or design spectral acceleration or site-specific or whatever target spectrum that you're taken, multiply that with this effective square divided by, because displacement, spectral displacement scales as 1 over omega square times spectral acceleration. So 1 over omega is basically 2 pi by time period. So that's what you see here. And then as I said, performance point with a couple of modification factors depending on the height of the structure, ductility of it, and things like that. There are a couple of coefficients involved on top of the spectral displacement that you estimate that gives you the performance point. So the economic losses were computed in this fashion, where this particular quantity, the front is the regional cost multiplier. Because we don't have enough data, we have taken uniform regional cost multiplier. But these three parameters here, they have to do with the built area, damage probability that you estimate from your fragility stuff, and this has to do with the replacement cost. So replacement cost table I've shown, damage probability, fragility you can compute from IDA or other methods, and built area is anyway known for your structure. So it's the product of these three summed over all the occupancy types, building topologies, and the damage states multiplied by regional cost estimated for each region. It's a very simple math calculation. So, of course, risk has to depend on the hazard level. So the hazard level that we have used for the 10% probability, which is 475 written period, and the 2% probability in 50 years is shown on the right here. And the first row has to do with the PGA, second row has to do with the 0.3 second spectral acceleration, and last row has to do with the 1 second spectral acceleration. So these are two asymptotic, two pivotal time periods in most building codes. Nowadays, for short period, you see 0.2 in terms of 0.3, but 1 second has not changed much. And PGA is, of course, the 0th time period asymptotic limit of your responsibility. So the hazard level has been taken, and we computed the risk in terms of economic losses for each Indian state. Red is pretty dangerous. There are millions of dollars. So basically, it's even going into billions here. So these are the districts here that we found from our kind of scenarios that we've done that can be pretty dangerous. But there are also these districts here that show second to the dangerous kind of condition, and particularly these two districts here, they are actually very far away from the Himalayan falls here. So still they experience a lot of economic loss. So this is something to thought about. The governments need to plan there. They have a state disaster board management. They may want to retrofit the buildings, improve the soil conditions, or things like that. Green is pretty much safe. Yellow is a little bit we have to worry about. We're done also for Delhi NCR. This is published in 17 WC conference. Unfortunately, it didn't happen this year. It may be happening next year. But we've done a similar thing as what we have done for Indo-Gangetic Plain. We've done similar computation for Delhi, national capital region of Delhi. That what's shown here is the hazard level that was considered. For example, PGA is more high here, but as you go to higher time periods of spectral acceleration, you see red shifting to the right side, districts on the right side. So economic losses, casualties, and damage probability are also shown here. Seismic risk for Delhi NCR. Most economic losses, if at all they happen, we see them over here. Of course, the margins are not much. That's probably because Delhi is fairly stable. As we've seen in the keynote lecture, there's no history of more than 4 or so high magnitude, except for 1 or 2 outlier cases. But anyway, the key take-home message here is highest economic losses also in this region. So basically, that's all I've got, and I think I've also run out of time. About 10 minutes, and I would be happy to take any questions.
Thank you so much, Dr. Somala, for this very interesting presentation. And I think we can open the floor to questions. I think many, I cannot see the comments online. Okay, waiting for questions to come from people online. I may start with my own questions, if you don't mind. So you mentioned about the use of different scenarios. So specifically 3 scenario earthquakes were considered in your assessment. So which kind of models you used? Maybe I missed this information.
Model as in the rupture model?
The models were to simulate the scenario earthquakes. We model 3 event scenarios, if I'm right.
Yes. So these are basically taken. The region is considered mainly in the seismic gap region, and we have these 2 extremes. A couple of them are considered as the extreme cases, and one is somewhere in the middle. As I said, the details of faulting and the rupture, they don't matter much in terms of the final end result. But yeah, the scenarios are considered typically in these locations. I'm not sure if that's what you were asking.
Yeah, I was curious to understand that a little bit better. You mentioned that the role of deep strike and the depth of the scenario earthquake is not really relevant for the final assessment of damage. Is it possible that this kind of this limited sensitiveness to fault parameters is due to the model you use to simulate to model the scenario earthquakes? Maybe the models do not allow to consider properly, for instance, the directivity of wave propagation due to source effects.
Not really. Actually, the reason here is that there's not much variation in the Himalayan context. Himalayan faulting is fairly fixed. But if this were to be for the northeast faulting is really complex, and in addition to that, there are also the Shillong plateau tectonics with all these transverse faulting that Professor Kayal and others have published a lot in the past. So there can be some influence of those focal mechanism parameters as well. But for this Himalayan context, the variability of these things is not much. Mostly these are the Himalayan thrust faults that matter, and their strike dip rate haven't. But the source location did matter. Source location, how far away or whether you're close by to the region, that of course does matter. But the faulting did not matter, not because that we cannot capture the rupture details in our rupture model, but it's because Himalayan faulting has very little variability there to handle. If it was some other region, yeah, maybe the sensitivity study would have given some other parameters to be more dominant.
I think there are questions from the floor. Okay.
How to scale the ground motion? Yeah, so scaling is one. The first method is a simple scale factor. Scale factor applied at the fundamental time period of interest, where you want to scale the spectrum that you have to the target spectrum level. Simple scale factor at that region. But more advanced ones are based on time frequency transform, violet transform based matching. You will see RSP match certain codes. Seismosoft also has one, something called Seismo signal, Seismo match, where they match the ground motion to the target spectrum that you have. So one really needs to go into the frequency domain or wavelet domain to do more advanced matching. But even the first order matchings are just based on the simple scaled matchings. So near fault earthquakes. Well, near fault stations is a term that we use. Near fault for the building context, how close is your building or how close is the earthquake data to the structure? So codal provisions nowadays have defined this thing. Of course, this can vary slightly based on what codal provision you are looking at. But as a term here, near fault has to do with, if you're talking about more than 7 magnitude earthquakes, if you have any of that sort, you can go up to 15 kilometer regime. If you're talking about 6.5 and above, you can go, if you have recordings within 10 kilometer distance, they are useful. If not, you may have to look for some other region. But there are also other suits of ground motions that many folks have, you'll find in literature. LMSR, low magnitude, small distance, large magnitude, small distance, or there's also NGA West kind of suits. There are also pulse-based ground motion suits. So each researcher is nowadays coming up with their own suit of ground motion. And some of them even have tens to hundreds of such earthquake data. So yeah, near fault basically in short means you're in 10 to 15 kilometers of regime for 6.5 to 7 and above magnitudes. Next question.
So I think there are no further questions. We can conclude the session.
Okay. Great, thank you. First of all, I want to thank Professor Kayal and Professor Seema Ghosh for inviting me for this. And thanks to Antonella for chairing this session.
Thank you, sir, for your nice presentation. It was nice presentation, sir.
Thank you.
Yeah, thank you, sir. Thank you so much for the edifying session. I also thank Professor Antelina Person for chairing the session.
Okay, I guess next session I am chairing.
Yeah, so you'll be
Yes.
chairing the next session. If everybody is okay with the thing, we can start the next session immediately, or you want to take some break.
Yeah, Pooja, let us
Yeah,
start
yes,
at scheduled time because some
Okay.
participants they might be waiting for scheduled time. So let us start
Okay.
at scheduled time.
Yeah,
And
let's
by
start
this,
at schedule.
Yes.
for this time, let us take virtual visit of NIT Agartala.
Yeah, sure, ma'am, we can take. Yeah, let's start the next session at 12:10. Thank you.
Yes.
ASSHEE International Workshop was formulated in 2019 by NIT-Agartala through an international collaboration with Russia, Finland and Italy. It achieved an overwhelming success from the students, young scientists, engineers and professionals, not only in Asiatic countries, Asian countries and African countries like Nigeria, but also in developed countries like Russia, Finland, Italy and Japan. The ASSHEE is now a phenomenal international platform to exchange knowledge, expertise and experience for benefit to the society, particularly to the young students, researchers in the field of earth sciences, earthquake engineering, civil engineering and seismic hazard mitigation. NIT-Agartala reckons you to join ASSHEE 2020 for a wholesome experience in the field of advanced seismology, seismic hazards and earthquake engineering.
Welcome back, everyone. Moving forward to the second technical session of the day, we have Professor Rubin Thatabosian and Professor Vera Bukava. Both of them will be delivering lecture on current practice of seismic hazard assessment. I introduce Rubin sir. To introduce Rubin sir, he is our guest of honor for ASSHEE 2020. He is currently head of Seismology Laboratory, Institute of Physics of the Earth, Moscow. He is also vice president of Asian Seismological Commission. And Professor Vera Baikova is one of the leading researchers of Russian Academy of Science, Moscow. Before handing over the session, I request Dr. Sumendranath Somala sir to chair the session.
Vera will start and I will continue after her, so we will share the time. Please, Vera.
Okay, I'll try.
Yes, ma'am, you can start.
Yeah, I try to, yeah. Okay, can you see my slide?
Not yet. You have to share it.
Just a minute. Okay. And now?
Yes, it's arrived.
Okay, everything is okay. Okay, let me start. I don't know good morning or good afternoon, but I want to say that it's a great pleasure for me to participate in this workshop for the second time. And today we will speak about the current practice of seismic hazard assessment, or being more exactly, of this practice being applied to nuclear installations. We shared our lectures and Professor Rubin Thatabosian has kindly offered me the part one, in which I would like to tell you about the safety guide of the International Atomic Energy Agency, including some technical problems, and including the creation of databases, evaluation of the ground motion hazards, and probabilistic seismic hazard assessment and its typical output. And then in part 2, Ruben Tetevasyan will tell you about the problems that are still unresolved and will attract your attention to some of these unresolved problems. Why do we want to speak about the nuclear installations? In 32 countries of the world, there is about 200 nuclear power plants. The total number of operable power reactors increases 400. And additionally, 55 reactors are under construction, more than 100 is planned, and while more than 300 reactors are proposed. As for India, nuclear power is the 5th largest source of electricity in India, after coal, gas, hydroelectricity, and wind power. Presently, India has 7 nuclear power plants in operation, with a total number of active reactors of 22. And 7 more reactors are under construction. If we look for the distribution of operable power reactors by countries, we see that India takes the 7th place in the world. And if we look for the same distribution of power reactors under construction, we'll see that India takes the 2nd place in the world, only after China. And what to deal with this? Because the main goal of all operational power plants and power plants under construction is the safety of their operation. And how can we achieve this goal? And this is the common deal of engineers and seismologists. Because different countries have different building codes and norms. And the contracts to new built nuclear power plant assign the priority of these building codes and norms that should be applied in the project. At the same time, the regulator contracts a number of experts from different countries and organizations in order they join the technical integration team, whose goal is to made all necessary studies, investigations, calculations, and so on, that should be independently of the norms and guides of the specific country. And this activity is oriented on the safety standards of the International Atomic Energy Agency, that are developed independently of codes and standards acting in the specific country. And today I would like to attract your attention to the safety guide number ASSHEE 9, which prescribes seismic hazards in site evaluation for nuclear installation. And if the last year I spoke about the basics of probabilistic seismic hazard assessment as presented in the textbook, I would like to show again these classical textbooks, internet resources, and also some PSHA softwares. And this year, I would like to show how these theoretical bases are implemented in the practice using the standards of the International Atomic Energy Agency. At first, some necessary remarks. Although this guide was published more than 10 years ago, presently we just follow it because standards do not change so quickly. And unless it is updated, we should follow these recommendations and standards. At first glance, it seems it gives very general recommendations, but at the same time, if you look more accurately, it prescribes very definitely what should be done and what procedures and studies and investigations should be carried in seismic hazard assessment for nuclear installations. And the third necessary remark that due to our obligation with contractors, I do not show you today the results of our current studies, and instead I use the published data that illustrate these techniques and what will I say. And these published data concern the nuclear power plant in South Africa and in Brazil. If we look on the structure of this guide, we'll see that it's rather close to what I showed you last year about the technique used in seismic hazard assessment in general technique, including the creation of the initial databases, development of the models of seismic sources, ground motion prediction equation selection, construction of the logic tree, the PSHE itself, with the results as hazard curves and a unified hazard response spectra at the conditional bedrock first, and then at the free surface using the site response analysis. So we'll start. At first, we should carry out and implement the geological, geophysical, and geotechnical database. This database includes at first regional investigations, and the size of this region may vary depending on the geological and tectonic setting, and its radial extent is typically 300 kilometers. Here you see the examples of South Africa and Brazil. Next scale of investigations is near-regional investigations that should cover generally 25 kilometers in radius around the site, but the dimension should be adjusted to reflect the local conditions, the specific local conditions. The next scale is the site vicinity investigations that cover an area of a radius of not less than 5 kilometers, and site area investigations. These investigations are very important, and the primary objective of them is to obtain the detailed knowledge of the potential for permanent ground displacement phenomena associated with earthquakes, and to provide information on the static and dynamic properties of foundation materials, such as P-wave and S-wave velocities, to be used then in site response analysis. The next step is the construction or completion of the seismological database that should include all pre-instrumental data, and moreover, they should be collected extending as far back in time as possible. And paleoseismic and archaeological information on historical and prehistoric earthquake also should be taken into account. All instrumental earthquake data should be collected, and with all the parameters that I note with small letters. And another important point is the project-specific instrumental data. It is recommended to install a local network of seismographs, and it's very interesting because it's not very often been that the minimum monitoring period to obtain meaningful data for seismotectonic interpretation is at least several years for the region of high seismicity, and is much longer for the regions of low seismicity. The next necessary point is that this local network should include also strong motion instruments. This is the examples of the corresponding seismological databases, I want to pay your attention to the period of observations that exceeds more than 300 years. And also, I would like to mention that all magnitudes should be in catalogs used to them in this database should be unified, and the most preferable nowadays is the moment magnitude. The link between these two databases, namely the geological, geophysical, geotechnical, and seismological, is a regional seismotectonic model, which should be based on a coherent merging of all these databases. And in the construction of such a model, all relevant interpretation of the seismotectonics of the region that may be found in the available literature should be taken into account. And the maximum potential magnitude associated with each seismic source should be specified, and uncertainty should be prescribed by a discrete or continuous probability distribution. Now we go to the evaluation of ground motion hazard. It is section 5 of the safety guide, where it is stated that the ground motion hazard should preferably be evaluated by using both probabilistic and deterministic methods. When both these methods are applied and the results are obtained, then deterministic assessments can be used as a check against probabilistic ones in terms of the reasonableness of the results, and particularly when small annual frequency of accidents are considered. And the probabilistic results allow deterministic values to be evaluated within a probabilistic framework, so that the annual frequency of accidents of each spectral ordinate is known. It is very important that in hazard evaluations, all uncertainties, both aleatory and epistemic, should be taken into account. Now, a few words about these uncertainties. The aleatory uncertainty is uncertainty inherent in a phenomenon, and it is taken into account by representing the phenomenon in terms of a probability distribution model. And we can, beforehand, I want to tell that this uncertainty is been applied intrinsically explicitly in the ground motion prediction equations. And the other kind of uncertainty is the epistemic one. This uncertainty is attributable to incomplete our knowledge about a phenomenon which affects the ability to model it. And this uncertainty is reflected in a range of variable models, multiple expert interpretation, and statistical confidence. And it is usually treated in seismic hazard analysis with the use of logic tree. Now we came to the characterization of the ground motion, and this is made by the use of the ground motion prediction equations. And you see in the paragraph 5.6, this is called by the attenuation relationships, but this is just due to follow the earlier practice. And these ground motion prediction equations describe the ground motion as a function of some parameters, the main of which are magnitude, distance, and some other. I really like this slide, and I showed you it last year. There is a lot of ground motion prediction equations now in the world. The total number reaches almost 600. And I would like to acknowledge John Douglas, who made this tremendous work for many years and collects all ground motion prediction equations. This is some parameters that are involved in modern ground motion prediction equations. And instead of magnitude and different measures of distance, they also include down deep width of the fault rupture plane, depth to the top of co-seismic rupture, depth to the bottom of the seismogenic crust, and some other parameters. And in spite of the fact that the number of these parameters is so much, we should mention that the uncertainties in ground motion prediction equations do not reduce. Section 6 tells us about the methodology of the probabilistic seismic hazard analysis. And how can we do this? This analysis should make use of all the elements and parameters of the seismotectonic model, including the quantified uncertainties. The probabilistic seismic hazard analysis is implemented using in mathematical form the integral, but for calculations we change the integration over sums, and this general expression includes the activity rate, ground motion prediction equations, and probability density functions for magnitude and distance. And the results of the probabilistic seismic hazard analysis are typically displayed as the mean or median annual frequency of exceedance of measures of horizontal and vertical ground motion that represent the range of periods of importance with regard to structures, systems, and components. An acceptable method for propagating the epistemic uncertainties, as I saw, through the probabilistic seismic hazard analysis is the development of the logic tree. You can just calculate all the branches of this logic tree, make the Monte Carlo simulation. And as a result of account of this epistemic uncertainty results in that the mean, 16th, median, and 84th fractal hazard curves are typically used to show the results. These hazard curves can be used to develop the uniform hazard spectra by such a way. And what is this spectra? It is a spectra whose spectral amplitudes have the same annual frequency of exceedance for the range of periods of interest with regard to structures, systems, and components. And for any selected hazard level, annual frequency of exceedances, and confidence level. In view of the complexity of seismic hazard analysis, an important question is the independent peer review. It should be necessarily conducted. And this review should not have been involved in other aspects that should not have vested the interest of outcome. The level and the type of peer review can vary depending on the application form, but it is necessary that it should address all parts of the seismic hazard analysis, including the process of analysis and all technical elements, for example, seismic source characterization, ground motion estimation, the methods of seismic hazard analysis, quantification, and documentation. And peer review panel should include the multidisciplinary expertise to address all technical and process-related aspects of the analysis. The purpose of this review is to provide the assurance that a proper process was conducted, and the analysis had addressed and evaluated all epistemic uncertainties, and the documentation is complete and traceable. And what is the typical output of the probabilistic seismic hazard analysis that is needed and is prescribed by the safety guide? This is the mean hazard curves, which is what means the mean annual frequency of accidents for each ground motion level of interest associated with a suite of epistemic hazard curves generated in the probabilistic analysis, and fractal hazard curves that are usually 5%, 16%, 50% are median, 84% and 95%, if unless is specified in the work plan. These hazard curves are used to build a uniform hazard response spectrum that should be reported for annual frequencies of different accidents and for different fractal levels. Then, after you obtain these curves, you can make magnitude distance deaggregations that quantifies the relative contribution to the total mean hazard of earthquakes in the specified magnitude distance range. From magnitude distance deaggregation results, you should find the mean and model magnitude and distances, and also you can do the seismic source deaggregation. If you consider the hazard at the site as a combination of the hazard from individual seismic sources modeled in probabilistic analysis. Aggregated hazard curves are used to combine these curves to preserve the diversity in shape of the original curves. And for the purpose of engineering analysis, the very important issue is the earthquake time histories that are required, and they should be consistent with the target response spectrum. This is briefly what I would like to say and to tell about the International Atomic Energy Agency Safety Guide. And this approach is now classical and is commonly used for seismic hazard assessment, particularly nuclear installation. And it prescribes our activities in order to operate the safety of the operational nuclear power plant units and power reactors under construction. The very important issue is also that the engineers and seismologists should work together. They should have a very good contact. This is all I want to say. And now I kindly give the word to the Professor Ruben Tutevasyan, because in spite of the fact that we know what procedures should be done, the nature of earthquakes is very complicated and different, and very many unresolved problems are still exist. Thank you.
Okay, thank you. Can I continue?
Yes, sir, you can continue.
So I have to share the screen.
Yeah, I close.
Okay. Share screen, and just a moment. I have to make a choice for this one. So can you see the presentation now?
Yes, it's coming up. Now it is visible.
Okay. Then I start. Well, you just have seen presentation on current practice of seismic hazard assessment, or more precisely, I said the probabilistic approach to this problem. But how much adequate it is? Well, in seismic hazard assessment, earthquake statistics is mostly used. For example, very well known Gutenberg-Richter law is a basis for hazard assessment. But individual earthquake is described in a rather primitive manner in such statistics. Mostly, the magnitude is taken into account. Well, in modern GMPs, some more physically meaningful source characteristics are used. For example, the stress drop. But as it is rarely known, especially for a whole set of earthquakes, which has to be analyzed, it is often taken as part of the epistemic uncertainty. And the question still is, what really controls the impact of earthquakes? Of course, I am not going to demonstrate or to show all the aspects of this problem, but let us address to observations to see some specific issue. Let me see here. Okay. So the two stars are epicenters of Spitak and Racha earthquakes. They are the largest seismic events in the Caucasus. And the slide also presents schematically tectonic setting of the region. And both earthquakes are located in the continental collision zone of Arabian and Eurasian plates. And so they are under compressional stresses. So from global point of view, they are in a similar situation. And also the magnitude of both earthquakes are practically the same. Macroseismic effect of these earthquakes were studied carefully, both in near and far field. Here is the assessment map of Spitak earthquake in the epicentral zone of future Racha earthquake, situated some 170 kilometers away. It was felt with intensity 4. So, and this is completely in agreement with the regional macroseismic field equation. In its epicentral area, the earthquake caused great damage and human losses. 10-degree isosseismal is drawn based on observations in 9 localities. And it is not just one outstanding or exaggerated report on a macroseismic effect, which support this high intensity degree. Well, and now let's see the other slide. And this is the isosseismal map of Racha earthquake. Intensity of shaking from its source at large distances is practically the same as from the Spitak earthquake. So far field effects is the same. And in particular, in the epicentral area of the Spitak earthquake, it was felt as intensity 4 shaking. But effects observed in its epicentral area were not more than 8-9 degrees. And this could not be ascribed to subjectivity of intensity assessment. Well, we all know that some subjectivity always inherent to intensity assessment, but in this particular case, due to a short time interval between seismic events, practically the same expert team made both macroseismic surveys. So at least they follow the same methodology of and same practice of intensity assessment. Well, of course, isosseismal map already contains a big deal of interpretation. So the true data is observed macroseismic effect. So let's have a look at it. And this slide shows macroseismic effect in epicentral area of Racha earthquake. Damage associated with Racha earthquake is due not to intensity of shaking itself, but to secondary effects like landslide and rockfalls. And I have to stress that the earthquake occurred in mountainous region after it was end of April, after the snow melt. And so the slopes were very wet and vulnerable for such secondary effects. And this was not the case of Spitak earthquake. Collapse of all types of constructions occurred in the epicentral area. And the difference in intensities in the epicenter zone could not be explained by vulnerability of constructions. Again, we all know that vulnerability of constructions is an important issue and very difficult to take correctly into account this factor. But also true that quality of constructions was in general rather poor in Armenia, where the earthquake occurred. But the construction types and in towns and construction traditions in rural areas in Armenia and Georgia, where the Racha earthquake occurred, are practically the same. I would like to remember you that both these republics were in Soviet Union at that time of earthquake. So all buildings were more or less built under the same design. So just to summarize this part, the difference in intensity of epicentral areas of Spitak and Racha earthquake, which reaches, by the way, 2 degrees, and it is a huge difference, is objective and could not be entirely attributed either to vulnerability of constructions or subjectivity of assessment. So let's try to find out possible reasons for this mentioned difference. Well, first of all, let's have a look at seismic history, because from the very general assumptions and from very general view, we can assume that peculiarities of seismic regime can give a hint on a character of energy accumulation and release. So strong earthquakes are not known either for instrumental or for historical times in the epicentral areas of both seismic events. But trenching after Spitak earthquake revealed traces of 2 paleo-earthquakes. These are these blue stars. In Racha epicentral zone, special studies to find paleo-earthquakes were not carried out, but paleo-earthquakes are well known in neighbored areas of Great Caucasus. Okay, now let's have a look at earthquake sources. I mean the fault plane mechanisms, because as it was also said by Vera, modern GMPs, they took into account earthquake mechanism because this is one of the important factors which influence the acceleration. According to CMT solutions, both sources are thrust with more in case of Spitak and less in case of Racha pronounced strike-slip component. But frankly speaking, this difference is negligible. So we can say that 2 earthquakes, both earthquakes are characterized with more or less the same mechanism. So let's try to evaluate somehow the complexity of sources. This is not expressed as a simple parameter, but nevertheless we can have some understanding of it, because it is one can expect that the source composed by a set of sub-events will be enriched by destructive high frequencies. Well, detailed view reveals that both sources are complex, and this can be found in teleseismic records. Here is the slide showing the modeling of using body wave records at teleseismic distances, and also in spatial distribution of seismic regime parameters. Here you can see the Gutenberg-Richter B value, which is mapped based on earthquake aftershock catalog. And also there are some graphs which demonstrate level of clustering. So both source zones are characterized with similar history, both have similar mechanism, and both sources are complex. So, but finally, is there something different in both earthquakes? Well, the first and very important difference is that Spitak earthquake was accompanied by surface faulting, meanwhile Racha was not. Significant difference can be found also in the pattern of spatial distribution of aftershocks. Spitak earthquake aftershocks occurred in narrow zone compared to the aftershocks of Racha earthquake, which occupy much wider zone. And I'd like to stress that this is not because of location accuracy, because this is the first thing to come in one's mind is that it is artifact. But aftershock recording was done on a very dense temporary network, which were installed thanks to the cooperation of different seismological organizations from Russia, France, and the United Kingdom. So the number of seismic stations in the epicentral zone in case of Racha earthquake were about 70. So this guarantee high data quality, or well, okay, at least the compatible data quality. And for making the maps, both aftershock catalogs were filtered to have the same lower limit of accuracy. So distribution of aftershock cloud in narrow strip in case of Spitaki earthquake suggests that the formation during main shock were localized. Meanwhile, dispersed deformations accompany Racha earthquake. So I made here a summary of features which are common for both earthquakes. Actually, this summary table in this part not very interesting because it demonstrates what features are in common. This is they are both under compressional regime, both have characterized with similar seismic history, and mechanisms of both earthquakes is more or less the same depth. I didn't tell it, but on the slide it was indicated the depth of the earthquake. And source complexity, again, is more or less the same, but then comes the difference. And the most striking difference is that surface faulting occurred during Spitaki earthquake. So here all differences are highlighted in red, and not only the surface faulting, but also the deformation type, which can be derived from aftershock distribution, is quite different. During Spitaki earthquake, it was much more localized. But is it possible to predict occurrence of surface faulting? Here, I put on the slide summary of observations on surface ruptures occurrences as function of earthquake magnitude. By the way, this in left part of the slide is the surface fault observed in epicentral area of the Spitaki earthquake. Okay, according to the plot, and keeping in mind that source mechanism of both earthquakes is reverse type, it is about 50% probability of surface rupture occurrence. If we do not know the fault type, then the anticipated probability for magnitude 7 earthquake to generate surface faulting is 70%. So again, we have to rely upon probabilities. So, but maybe the problem is not in probabilistic approach as it is, but the problem is what, which characteristics has to be considered in hazard analysis as being important. Well, frankly speaking, I don't know the answer. So I made some summary slide, in which I just put together the things presented in just now. So this is that Spitaki and Racha earthquakes in the Caucasus, having approximately the same magnitude, lead to significantly different shaking intensity in the epicentral areas. And the effect in the far field from both earthquakes is practically the same and completely in agreement with prediction of regional macroseismic field. And, epicentral intensity depends on occurrence of surface rupture and type of deformation, localized or dispersed. Localized deformations cause a higher intensity of shaking. And then comes the question, maybe we have to revise traditional PSHA approach such that impact of strong nearby sources has to be treated separately. And how to assess probabilities of surface faulting in advance and how to incorporate it is still open question. I am afraid that I mostly put questions instead of giving answers, but this is more or less in my understanding the true situation with hazard assessment. Well, and I would like to show the last slide. This is just to remember the wonderful event happened in Agartala 1 year ago. And can you guess which event I mean? This one. Okay, thank you very much. In my presentation, I touch only one issue, but this is mostly to give an example how difficult and how uncertain the situation with the current practice of seismic hazard assessment. Thank you.
So thank you, Professor Vida and Professor Ruben, for interesting talk on seismic hazard assessment. Examples from great error cases and low worker cases. So the floor is open for questions.
Could I make some comments?
Yeah.
Yeah, sure, sir.
Okay. I think it's very interesting, Ruben, to see that similar magnitude and similar mechanism as two different types of, intensities or the damage. Now, for most of the earthquakes, particularly in the ASSHEE region, in the shield area, in the interpreted zone, we don't see any surface rupture. And how we can, face such problem? Suppose for Bhuj earthquake, there was no surface rupture. For the Kilari earthquake, there was very little surface rupture, maybe about a kilometer or so, and that was also not continuous. But the Bhuj particularly, it is 7.7 or 7.8 magnitude earthquake. It has no surface rupture. And there are many examples where we don't find any surface rupture. Now, how we will take care of such type of events which has no surface rupture?
Okay, I think this is because the surface rupture is not the only feature which gives us information what will happen. For example, I just would like to make a clear difference between surface rupture and near fault location, because near fault is one thing, and surface rupture is something which is fall inside the class of this near fault cases. And in Bhuj earthquake, as you mentioned, surface rupture was not observed. But as far as I know, very important factor in that case of the Bhuj earthquake was soil conditions. There was, again, up to my knowledge, very high amplification of intensity due to the soil conditions. So this is what I mean actually with the presentation, that it is very important in each situation, in each case, to understand, to know what factor can be, let's say, important, which will destroy our traditional PSHA approach. The traditional PSHA approach, I would like to stress it, I have nothing against it. It is very good as a framework. But within this framework, we have to build some specific bricks. This is my general idea and the message that I would like to deliver.
Thank you so much. Thank you so much.
And I have seen some question. It was on the screen. How can we incorporate the paleoseismic results? Some rating is applied to how that has slip rate or slow slip rate, on the contrary. Well, paleoseismic results can be incorporated, meaning at least by putting them as an events in magnitude frequency or Gutenberg-Richter relationship, which in principle may affect this relationship, and the B value will be more, let's say, realistic than we can derive it only and simply from the historical and instrumental data. Okay, and I can see another question about the paleo earthquakes. As I told you, in the Spitak earthquake epicentral area, the same place, there were trenches digged across the surface faulting, and they found in these trenches two evidences of paleo earthquakes with similar magnitude. Well, of course, the magnitude evaluation is not very precise, but these were assessed like magnitude 7. So the same as the Spitak earthquake. And the problem is that this is very usual situation. When earthquake occur and you start to look for paleo earthquake, you find them. The problem is how to find them before the large earthquake occurred. And as for the Racha earthquake, there were no special investigations for the paleo earthquake, where trenches were not cut. Well, several reasons. One is the political, because the Soviet Union collapsed and no one worried very much about in those years the seismic hazard. This is one economic and political reason. And the second reason is that as far as surface faulting was not observed, it was not clear where to cut these trenches. The geologist needs a hint, and better, very good hint, where to cut the trench. Sorry, there's another question. So in India, the earthquake ground motion for the NPP by deterministic method. Well, this is clear, but you know that depending what you call deterministic method, because for example, in the SSG 9 guide, which Vera presented the beginning of our presentation, deterministic method also is described, but actually this is the same as probabilistic. The only difference in deterministic method, as it is described in SSG 9, that you should locate your source not in any place with equal probability within the source area, but to the distance which is nearest to the site. So practically all the other elements, like taking into account epistemic and aleatory uncertainties, is still valid. I don't know if something of this is used in India. I don't know the Indian law and the regulations in the NPP. This is one of the countries where we never worked before, though we work more or less everywhere. If the true deterministic approach is applied, I mean, one take a fault and make the calculations from this directly. Another problem arises that we never, practically never, I don't know, maybe India is the exception, knows the exact parameters of the fault to make calculations. So, and aleatory uncertainty is still there. because even in case of very similar faults, the response spectra can be different. Okay, and there is another question I see.
I would like to add a few words.
Okay.
If it is possible, because and concerning the next question, which is better, deterministic or probabilistic seismic hazard assessment, as I can see, I would like to say that you cannot use the purely deterministic assessment or purely probabilistic, because these approaches intersect in sometimes. Because, for example, if you use the probabilistic seismic hazards analysis, then nevertheless you should define seismogeological model of seismic sources. You should make some expert decisions of what model to choose, what earthquakes to choose, what ground motion prediction to choose. So it is, how to say, the part of determinism in your probabilistic approach. At the same time, the deterministic approach cannot be purely deterministic, because you should use, in any case, different ground motion prediction equations with their aleatory uncertainty. Sure, you can select from those which is more worse or something like this. But these approaches should be used together.
Okay, I think there is still time to answer another question I see on the screen.
Well, we have one
asking why earthquakes are rare in the area despite of all exploration and exploitation activity. I don't know if there should be any such relationship, because the exploitation of oil reservoir is more or less upper part of the crust, and the earthquakes are deep. No, I don't know why we should have so very strict relationships. Of course, one can suggest model, and maybe this model even will be valid about the fluid movement, penetration depths, and so on and so on. But I'm not sure that one should see direct link of such phenomena, which are very different level involved. I see that Antonella wants to comment.
Sorry, I wanted just to add something about deterministic and probabilistic approaches. I would like to mention that nowadays the scenario-based approaches are getting more and more feasible and popular. So it is possible to simulate earthquakes and propagation without relying only on ground motion prediction equations, and by doing many parametric tests, changing the source features, the structural models, and all these parameters, and then applying a statistical approach to put together this information, you can get also some new, let's say, view of the hazard, which is not necessarily a full alternative, but at least complementary to existing methods. And maybe in this way, we can use better our physical knowledge that we acquired over the time. Thank you.
Yeah, very.
Thank you. Yes, this is true. There are much more options nowadays than pure deterministic or probabilistic approach.
Okay, we have one more question. How do we select maximum magnitude for aerial seismic source based on geology?
I understand what is the, if I understood correctly, the contradiction which is mentioned is that if we take, for example, rupture length and then using Wilson-Copper-Smith relationships, for example, Ranitin or Leonardo relationship, we can evaluate a maximum, well, not a maximum, the magnitude associated with the earthquake, and then assess the maximum. It is clear, but how to do it for the aerial sources? As far as I understand, for aerial sources, one should select a floating earthquake, which can occur any place, and then to see which, if there is any structure which can fit it. And then also in such areas, when there is no possibility to link directly and simply the epicenters to some faults, is to mostly rely upon instrumental catalog data, earthquake catalog data. By the way, this approach is also approach based on observed seismicity is in use too.
So next question is by Rajiv Kumar. How do we decide the weightage for GMPs in logic tree?
Well, arbitrary. This is the first thing to say, and we can stop it there. But I would add also that for this, my preference personally is to give equal weights. Because if you know that some are much better than the other, then don't include the other. In my understanding, the best strategy is to include compatible things in logic tree. Otherwise, you will have an impression that all epistemic uncertainties are taken, but practically by weighting you press the most of them. So my preference is to rely upon equal weighting. Because this is the equal weighting reflects much better the true lack of knowledge.
So next question is by Saurav Chaudhary. How are paleo-seismic earthquakes ruptures the Himalayas?
Well, I should re-address it to Dr. Kayal, I think, about the paleo earthquakes in Himalayas.
Professor Kayal, you want to speak, or should we take the next question? I think you are muted, Professor Kayal.
Yes, I think we have to stop somewhere now. Maybe one more question you can take up. Yeah.
Okay, this is the last question from Mr. Nisar. What is the latest technique to make the world structure earthquake?
Well, this is out of scope of my interest and knowledge, but designers, they I think have something, but I don't want to give misleading comments to the problem.
I mean, as an engineer, I can comment a bit. There is a technique called retrofitting. Retrofitting is what you do as long as you know it's cost effective. Instead of demolishing the structure, you try to make it stronger. There are various techniques, steel jacketing or to appropriate sources on that. I guess with that, we conclude this session on Professor Ruben and Professor Veera on hazard assessment. We take a 1-minute break before we move on to the next session.
Yeah, we'll take a small short break.
Now will be lunch.
Yeah, we can head towards the lunch. Before that, I thank you, Professor Rubin Tatevosian and Vera Baikova, for an elucidating session on current practices on seismic hazard assessment. I also thank Dr. Surendranath Somala for chairing the session. We can now take a small break for 20 minutes and we can schedule a next session for 1:30. Thank you.
Thank you. Bye. Thanks a lot.
Bye. Bye.
Thank you so much. Thank you, Beda.
The ASSHEE International Workshop was formulated in 2019 by NIT-Agartala through an international collaboration with Russia, Finland and Italy. It achieved an overwhelming success from the students, young scientists, engineers and professionals, not only in Asiatic countries, Asian countries and African countries like Nigeria, but also in developed countries like Russia, Finland, Italy and Japan. The ASSHEE is now a phenomenal international platform to exchange knowledge, expertise and experience for benefit to the society, particularly to the young students, researchers in the field of earth sciences, earthquake engineering, civil engineering and seismic hazard mitigation. NIT-Agartala recommends you to join ASSHEE 2020 for a wholesome experience in the field of advanced seismology, seismic hazards and earthquake engineering.
Хороший футбольный матч.
The ASSHEE International Workshop was formulated in 2019 by NIT-Agartala through an international collaboration with Russia, Finland and Italy. It achieved an overwhelming success from the students, young scientists, engineers and professionals, not only in Asiatic countries, Asian countries and African countries like Nigeria, but also in developed countries like Russia, Finland, Italy and Japan. The ASSHEE is now a phenomenal international platform to exchange knowledge, expertise and experience for benefit to the society, particularly to the young students, researchers in the field of earth sciences, earthquake engineering, civil engineering and seismic hazard mitigation. NIT-Agartala reckons you to join ASSHEE 2020 for a wholesome experience in the field of advanced seismology, seismic hazards and earthquake engineering.
Okay.
Слышишь?
Yes, I think we can start. Puja, may come do the announcement. Yes, Puja, I think we can start. You can make the announcement. Yes, he has come. Yep.
Yeah, welcome back, everyone.
Yes, come. Yep.
Sorry for the inconvenience. Welcome back, everyone. Can I continue now?
Yes, please.
Am I audible to everybody?
Yes, yes, you are audible. Yes. I think you have some network problem, but you can start when you are online. Yeah.
Am I audible to everyone?
Yes, yes,
Yeah.
yes.
Coming back to the
Yes,
final
please.
technical session of day 2, we have a session.
Yes, you are audible. Yes.
Um,
I think you have some network problem.
yeah.
You can start
Yes, sir.
when you are.
Uh, coming also research Italy. She is also adjunct professor at Physics Department at University of Trieste, Italy. I request Dr. J.R. Kyle, sir, to chair the session.
Thank you, Pooja. Thank you for your kind announcement. Now I would request our good friend and now good speaker,
Sir,
Professor Antenola, to take over and start her lecture. Yes.
Thank you so much. Let me start sharing the screen. Let's see. Let me start sharing the screen. Let's see.
Yeah.
Okay. Please let me know if you can see the full screen slide. Can you see it? Please let me know.
No, at the moment, no.
Not yet.
Is it visible?
No.
No, not yet.
Let's try again. Is it visible now?
No. You have to go to share.
Yeah, it seems. Okay, let's try a different option.
There is a share option.
Yes. Can you see my screen now?
Yeah.
Yes.
Yes.
Okay, fine. Perfect. Okay, so during the next hour, we'll try to summarize some new results we received in the analysis of earthquake clusters and background seismicity that may be relevant in connection with what was mentioned in the earlier presentations, especially the one by Ruben and Vera. So all these methods for seismic hazard assessment, they assume some occurrence model for earthquakes, and they may also deal with the cluster catalog or deal with the specific properties of aftershocks occurrence. So the results I'm going to present hopefully will be useful for seismic hazard assessment, and it's not just a statistical exercise we did with that. The work I'm going to present has been carried out in collaboration with colleagues from Italy, CNR, from Japan, from Russia, and from Algeria. So basically, what we do when we try to identify earthquake clusters is targeting two scopes. One is the declustering of the catalog itself, so remove the aftershocks and these clustering properties in an attempt to make the remaining data Poissonian, so as to meet some standard basic requirements of several models for seismic hazard assessment. Another reason to identify and analyze the earthquake clusters is to study the clustering features, to quantify, to characterize them, and try to relate them with the physical properties of the crust, or to model them in an attempt to study their evolution and to incorporate again this information in seismic hazard and risk assessment. Anyway, in spite of the analysis and identification of clusters is widely applied in many fields of seismology, many seismological investigations, still there is no univocal definition of what an earthquake cluster is. And therefore, different methods may lead to different identification and classification of the and characterization of the clusters. So for this reason, we investigated the way they partition the catalog to quite recent and advanced methods, namely the nearest neighbor approach and the stochastic declustering approach based on ITA's model. And we use these two methods because both of them allow for a data-driven identification of seismic clusters. It means the parameters are set on the specific data set. And moreover, both of them permit to define and characterize the internal structure of individual clusters. Based on the cluster, the catalog, and the clusters identified, we will explore the features of background seismicity and the features of the clusters themselves, with the aim to capture some space and temporal patterns of earthquake occurrence. And for this purpose, we will focus our attention on the catalog for northeastern Italy, which corresponds to the area of transition between the Alps and Dinaric mountain ranges. So let's start from the description of the method. I will start from the nearest neighbor approach, which is a pretty recent new approach for clusters identification. And the method is based on the nearest neighbor distance eta, which was introduced by Bayesi and Pachutsky in 2004. And this distance basically defines the connection, the relation between events in the space, time, and energy domain. So here you can see how the distance eta is defined between two earthquakes, an earthquake J and an earlier earthquake I. So basically the distance eta is the product of the interevent time between the two events, the spatial distance between the epicenters, which is scaled by the fractal dimension of epicenters in the area, and by a term which is depending from, it's related to the Gutenberg-Richter law. This B here is the B value and accounts for the energy of events. The property that of the eta distance is that it can be expressed as the product of rescale time t and rescale distance r, and in this way it can be let's say represented as a bimodal let's say distribution in the rescale time and rescale distance domain. Well, let's see how this distance works when applied to simulated seismicity. If we take a Poisson sequence of earthquakes, we see that the distribution of the nearest neighbor distance has a unimodal distribution with a specific location along the distances. Similarly, if we analyze a single aftershock series, we again have a unimodal distribution of distance eta, but with a different location, so it's centered in much smaller values. If we apply this nearest neighbor distance to a sequence generated by ITA's model, which has both the Poissonian background and the aftershock series, then we get a bimodal distribution. And this is also reflected in the two-dimensional distribution in rescale space and rescale time that I just introduced. So we can see that in both one-dimensional and two-dimensional distribution, we can put a boundary, a threshold, which separates the two modes, one corresponding to the cluster component and the other one to the Poissonian background. Coming to real seismicity, and these are the distributions we obtain actually from real seismicity in central Italy. You can see that the distribution of eta distances is actually a bimodal one, and we can define, based on a Gaussian mixture model or even by hand, we can easily put a boundary separating the two modes. And also in the two-dimensional distribution of distances in terms of rescale time and rescale distances, we have a bimodal distribution where one part corresponds to a background component where the links are pretty weak, and the other part, the other mode is corresponding to cluster seismicity. So we can see that according to this nearest neighbor distance, it's pretty natural, the separation of between clustered and Poissonian or background component. So once we have defined the threshold, we consider the earthquake catalog. In the catalog, each event is connected to its nearest neighbor based on the distance we have introduced. And by putting the threshold, we can define the weak links, so those exceeding the threshold, and the strong links, those below the threshold eta that we have defined so far. And by dropping this connection, we can separate the clusters formed by earthquakes. So afterward, within a cluster, we usually define as the main shock the largest events, and the events which the earthquakes which precede it are called as the foreshocks, whereas the events that follow that, the main event, are the aftershocks. So this is, let's say, not, I mean, it's an assumption. We could define also in a different way what is the main shock, but this is quite a natural one. Well, it is important to note that besides the possibility to identify the clusters and separate the clusters, the method also allows to connect, to provide the structure of the cluster in terms of the links that connect individual events. And you can see here that for two events with similar magnitude, you can have a pretty different structure. So in this case, most of the events are connected to the main one, whereas here they have a much more complicated structure, which is called a swarm-like, a kind of sequence where there is no dominating event. And this structure has been found to be related, or can be related with the physical properties of the crust. For instance, it was found that swarm-like clusters, so the one with a complicated internal structure, are occurring preferably in regions where we have high heat flow or presence of fluids, or let's say less rigid rocks. And this property also allowed to analyze induced seismicity, for which it was found that the injection of fluids is affecting the properties, the features of the clusters and their structure. So this is also a way to analyze the connection between the physical properties of the crust and the representations in terms of properties of the clusters. So how this method was applied in northeastern Italy. So we consider seismicity reported in OGS bulletins from 1977 to 2018. And in this area that you can see here in northeastern Italy, strong earthquakes occurred in the past. The last one was a magnitude 6.4 in 1976, but since then, only low to moderate magnitude events have been observed. The largest ones are magnitude 5.6 and occurred in 1998, and magnitude 5.1 in 2004. Both of them occurred in this area at the borders with the Slovenia. For this catalog, we analyzed the space and time completeness by comparing with global data sets and by analyzing the frequency magnitude distribution. And the conservative confident level of completeness could be set to magnitude 2, even starting from 1977. However, in recent years, the completeness is significantly improved down to magnitude 1.0 or at least 1.5. To estimate the parameters needed for the application of the nearest neighbor approach, which are, as I mentioned, the fractal dimension of epicenters and the B-value, we decided to resort to the unified scaling law for earthquakes, which you can see here, that provides a joint estimate of both parameters. Here you can see A is the level of seismic activity, B is corresponding to the B value, and D is the fractal dimension of epicenters within the study area. And this unified scaling law for earthquakes is a kind of generalization of the Gutenberg-Richter law, which allows to account also for heterogeneous distribution of epicenters in space. And well, we estimated these parameters at different, with different detail, but at the end, we sorted out, let's say, unique value, average value for the entire area, which is B equal to 0.9, and fractal dimension ranging from 1 to 1.1 in the region, which is a pretty low value if we compare with California, for instance, where fractal dimension is 1.4 or 1.5. Well, applying the nearest neighbor distance for this catalog, we observed that in the period from 1977 to 2015, which is the first part we analyzed, we have a significantly dominant component, Poissonian background component, and less evident cluster component. Going back in time, but reducing the completeness of the data, we can see that the cluster component is well visible here. But in the recent year, as I mentioned, we don't have significant earthquakes, very large earthquakes, and therefore the cluster component is, let's say, smaller than the background one. So after identifying the earthquake clusters, we compare them with those manually identified by experts in the area, especially for the two largest events which struck the region in the last 40 years, namely the two events magnitude 5.6 and 5.1 in Kobarid area. And what we could observe is that there is a pretty good agreement. You can see in red the manually identified epicenters of aftershocks, in green those identified by nearest neighbor, and this is the temporal distribution. They are in pretty good agreement. And also, if we compare with those identified by classical window methods like Gardner-Knopf or Urhammer, they are still, the nearest neighbor still works better, because, for instance, the Gardner-Knopf definitely overestimates the spatial and the temporal duration of the sequence. Similar observation was done also for the magnitude 5.1 earthquake in July 2004. You can see that there is a perfect correspondence between the epicenters of manually identified and aftershocks identified by nearest neighbor. Please note that this distance is less than 10 kilometers, where the earthquakes are highly concentrated. And also in this case, nearest neighbor works better than classical windows methods. But there is also another feature you can see here. Well, this is time, this is longitude, and these dots correspond to earthquakes. So this is a temporal representation of earthquakes occurrence. This is the full catalog with all events, where you can recognize the main earthquakes and their aftershock series. This is the cluster catalog by nearest neighbor. And here you can see that the cluster catalog by classical window method, especially the Gardner-Knopf. And you can see that the classical window method create evident gaps in seismicity. So we must be very cautious when analyzing background seismicity after this kind of declustering. We also did similar experiments in Central Italy, where we have much higher seismicity. And again, here you can see that this is the full catalog. This is the cluster catalog by the nearest neighbor. You can see that the clusters are removed, whereas the Windows method, either they create gaps in seismicity or they are insufficient in removing the aftershock. So in both cases, the background is not satisfactory provided. And this must be taken into account, especially when carrying out studies of seismicity in an area, for instance, when looking for seismic quiescence, where applying the Windows methods for the clustering may create artificial quiescences. And this method, the nearest neighbor, has been applied also in a recent study for Iran, where quiescence was investigated. And in this case, you can see the full catalog and the cluster catalog by nearest neighbor, which preserves the heterogeneity in space and time of seismicity, but still it prevents the creation of gaps, which could be misinterpreted. Well, of course, as I mentioned, the nearest neighbor is just one method for identification of earthquake clusters and for catalogs the clustering. We can also apply other methods. The most, let's say, used one and the most advanced one is probably the stochastic declustering based on ITA's model. This model is defined under assumption of stationarity and ergodicity of earthquakes, is defined as by the conditional intensity function in time and space, conditioned by the seismic history of the area, and describes seismicity as the sum of different components. This is the background component of seismicity, which is variable in space but not in time in this model, and a cluster component where we have a term which is characterizing the productivity in terms of aftershock, the temporal features of aftershocks occurrence, and the spatial features of aftershocks occurrence. So here you have the details of the distributions, but I just want to mention that there are these main elements. Well, based on this definition, we can define the background events as the independent one, the statistically independent events. And these events are referred as immigrants in the ITAS model. And based on this relationship, we can define, for each event, we can define a probability that it is an offspring of an earlier earthquake using this relationship, or we can define we can compute the probability that is just an offspring, or the probability that is an immigrant, which means a main event, background one. Given this definition, we can compose the cluster catalog as the set of immigrants, so independent events, and each immigrant has may have its offsprings, so the aftershocks or related events, which compose a random cluster. It is important to observe that according to the stochastic method, the cluster catalog is not unique, but it depends on the different clustering, the different probabilities you may choose, and you have different clustering scenarios. So, the model, coming to the model parameters, so here we have the parameters that are used by the nearest neighbor approach. As I mentioned, the B-value and the fractal dimension of epicenter, and the threshold eta, which selects the cluster from background component, whereas the stochastic declustering method requires many more parameters. And these parameters can be obtained by specific iterative algorithm, where maximum likelihood is combined with kernel methods, and therefore is quite, let's say, sophisticated either in terms of parameters and computational time to identify the parameters. And it's worth mentioning that the stochastic declustering is more, let's say, sensitive to completeness of earthquake data, because the parameters are conditioned to the seismic history of the region. And therefore, you need to have a good representative picture of past seismicity to define them properly. Here, you can see some representation, the total rate of seismicity, which is defined according to the stochastic declustering method, some clustering effect that is defined as the ratio between total rate and the background component and the total rate. And here you can see the distribution of probabilities of being, for each event J, of being a background event or belonging to a cluster. So if the probability is close to 1, the earthquake has a high probability to be a background event. If it is close to 0, then it is a triggered one. But we can see that there are also events with a less clear classification. Well, after applying this method to the same data set of northeastern Italy, we compare the statistics of the identified earthquake clusters, and we observe that the number of main shocks identified by the two methods are pretty similar. So the percentage of individual single events is around 45–50%. The number of main shocks is well comparable, around 89%. And the percentage of aftershocks, the portion of aftershocks, around 35–40%, which is quite small compared to other seismically active regions like central Italy, is also comparable. The better match between clusters identified by nearest neighbor and stochastic declustering is obtained for SD-max realization of the stochastic declustering. What is SD-max? SD-max is the realization which which is associated to the maximum probabilities relating each event and its offspring. So at each step of the simulation, we select the maximum probability. So we found that the stochastic declustering with maximum probabilities is the one providing the most similar clusters compared to the nearest neighbor. Well, how they compare, again, in space and time, the sequences we identify with the two methods. Again, we focus on the two largest clusters, and we see that, well, there is a pretty good match. The number of events is very similar. The associated events are almost the same. But for, let's say, in the NN, the nearest neighbor method, some events that are distant in space are also associated to the cluster, whereas the stochastic declustering method tends to associate more events which are distant in time and closer in space. But as you can see, the background seismicity obtained by the two methods are pretty similar. Here, the different events in the clusters are highlighted in red, but you can see that the large majority of earthquakes is properly, is classified in the same way in both methods. Well, given that now we have two catalogs, the cluster catalog by the two methods, nearest neighbor and stochastic declustering approach, then our question is whether the resulting catalog, the cluster catalog, is really a stationary Poisson one, or it may have different features. Well, I have to say that applying the classical test like Kolmogorov-Smirnov and Ran's tests to these declustered catalogs by both approaches, in both cases, seismicity turned out not compatible with the stationary Poisson process. Therefore, we decided to explore whether maybe a non-stationary Poisson process could be applied. And for doing this analysis, we resorted to the MMPP, Markov modulated Poisson process, with a different number of states. And in this model, essentially, seismicity is again modeled by Poisson process, but with different rates over the time, so non-stationary one. Well, we applied, let's say, models with different number of states, so 2 states, 3 states, and up to 4 states, and we could see that the model best fitting the both stochastic declustering and nearest neighbor sequences is the one composed by 3 different states. here you can see the representation over time. This is the probability at each time that the system is in one of the three states. One is high seismicity rate in red, intermediate rate in green, and low rate in blue. And you can see that the pattern identified for the two data sets is quite consistent, though the nearest neighbor provides more variations in the background seismicity, but the overall pattern is pretty comparable. And by selecting the maximum value of probability for at each time step, we could define the time intervals of moderate, low, and high seismicity in time. And we see that they are again pretty comparable for the two methods. And it is possible to observe periods of low seismicity, intervals T4 and T5, and a well evident period of increased seismicity, of high seismicity, which follows, but it begins a little bit earlier than the 1998 largest earthquake and lasts up to about 2002. Well, this here you can see the real seismicity, so the events which occurred during this time, and you can see that actually the Markov modulated Poisson process capture pretty well the features of observed seismicity, so the level of seismic activity. And we also compared these transitions that were identified by this MMPP model, and we found that they cannot be obviously related with changes in the network, in the detection system, but they really appear to be properties of background seismicity. And this is this method also provides the probability of transition from one state to another, so that we can estimate, given a time t with a specific probability, we can estimate the switch to the next state. But this predictive, let's say, model needs more testing before being applied. Anyway, to summarize, the study carried out in both background sequences by stochastic declustering and nearest neighbor approach highlighted that the background seismicity is non-Poissonian, is not stationary, and then we cannot model it when dealing with seismic hazard with a simple Poissonian model. And also the method permitted us to see that this feature is consistently identified by both methods, and therefore this property is not depending critically on the clustering method for the catalog. Well, now we have another property that we would like to consider, and is focused on the internal structure of the aftershocks. So up to now we have analyzed the cluster catalog. Now we focus our attention on the clusters themselves, and we want to see how different are the properties we can detect by using different techniques. So we decided to investigate the cluster characterization, which is allowed by the nearest neighbor approach and the stochastic declustering, because both these methods provide an internal structure for the earthquake clusters. The nearest neighbor by connecting each event to its nearest neighbor, and the stochastic declustering by providing probability for connection between different events in the catalog. Again, we explore the features of the clusters by relying on data for northeastern Italy. So when applying the nearest neighbor approach to the catalog of northeastern Italy, we observe that there are the two major clusters, which I already related with the two largest events, that actually have a pretty simple burst-like structure, internal structure, where the majority of events is directly connected, as you can see by these red bars. Most of the events are directly connected with the main shock. So the nearest neighbor event for most of them, for most of the aftershock, is just the main shock. But in other parts of the regions, for instance, in this area, which is characterized by thermal areas, high heat flow and presence of fluid, we observe clusters which are definitely smaller, but have a much more complicated internal structure. And this area is an area where typically swarm-like sequences are observed. So it seems that the nearest neighbor can capture these features. So our idea was to check whether also whether this structure is also identified by stochastic declustering. So let's consider here just one cluster, the one associated with the Kobarid earthquake in '98, which is the largest one. Here it is the structure of the tree of the cluster according to the nearest neighbor approach. You can see it's pretty simple one, umbrella-like. The configuration of the cluster, the structure identified by stochastic declustering with maximum probabilities, is also showing a dominant role of the main shock and also some secondary umbrellas. They are, let's say, it is evident that this one is more complicated, but really the main dominating events are the same. If we consider other possible simulations by stochastic declustering, you see that the complexity of the internal structure increases. This fact is essentially related to the definition of the stochastic declustering, which is based on ITA's model, epidemic type aftershock sequence model, which basically includes a multi-level triggering property, so where each event can generate its own aftershock. So this complexity is built in somehow in the stochastic declustering method. So by visual inspection, we can see how they are similar or different, but we want to quantify this complexity. And the first metric we use to quantify the complexity of cluster is the average node depth, which was proposed by Zaliapin and by my co-authors and myself in 2018, was applied to the Friuli Venezia Giulia seismicity. And basically, this measure is counting the distance between the leaves in the tree, in the chain of events, and the main shock. So here you have a long chain, so a large average node depth. In this case, most of the events are connected with the main shock, so the average node depth is much smaller. If we compare the structure of the tree obtained from stochastic declustering and nearest neighbor, we can see that in the stochastic declustering, we have a much more evident dependence of the complexity of the structure on the magnitude, whereas in the nearest neighbor, there are small events which have very large complexity, average node depth, and large events that are associated with a low complexity. And also the statistical distribution of number of clusters versus their complexity is pretty comparable, especially if we consider the realization of SD max, which is associated with the largest, with the maximum probabilities in the simulation. Since we found that this representation is really not sufficient, or maybe not sufficient to capture the different properties of the clusters, we decided to explore some centrality measures which are used in network theory to better characterize the internal hierarchical organization of the earthquakes in each clusters. And for this purpose, we borrowed some centrality measures, which I'm going to introduce, to define, to describe the individual clusters. So the let's say these measures are based on centrality scores. The centrality score is a property, is a quantity which is associated with an individual node in the cluster, so with each earthquake in the cluster, and measures, for instance, in the case of out degree centrality, a node has high centrality, whereas when it has many offsprings, whereas the closeness centrality gives the highest score for events that have the largest distance, the shortest distance from other events in terms of connection along the tree. Based on these centrality measures, we can define a centralization index, which is a global index characterizing the entire cluster, the entire topological tree. And this centralization can be defined both using out degree or centrality or closeness centrality. And what is important to keep in mind is that high centralization values, close to 1, suggest that there is a dominant event in the cluster. It means an earthquake which has most of the offsprings, or an event which is the closest to all the other events. On the contrary, if the index, the centralization index, is low, so close to 0, it means that the cluster has a more complicated hierarchical structure, swarm-like, or let's say with many relevant earthquakes in the structure. Just to exemplify, to provide some simple cases to better understand what is the meaning of this index, here you can see the very basic umbrella-like sequence for which both centralization, closeness, and out degree centralization is close to 1, is equal to 1, sorry. And this is the most complicated chain-like sequence, which provides centrality index close to 0. And here you have intermediate type sequences, which provide intermediate values of the parameters of the coefficient. And here you have a sequence where you have a double umbrella, whereas this is more typical sequence with many, let's say, long chains of events. So low values of centralization means complex structure. High values means burst-like, umbrella-like structure of the cluster. Well, by comparing systematically the clusters from nearest neighbor and the stochastic declustering in terms of out degree and closeness centralization measures, we can see that SD clusters, stochastic declustering clusters, are systematically lower than the nearest neighbor ones, according to both measures. This means that the SD clusters have a generally much more complex internal structure than the nearest neighbor ones, especially for the largest events, which are marked in red here. This is one is the 1998 earthquake, and this is the 2004 magnitude 5.1 earthquake, whereas this is a magnitude 5.1 occurred in 1977. So the stochastic declustering provides systematically more complex structure for the clusters, especially for the largest events, which reflects the multi-level triggering of property of the ITAS model. Given this observation, we decided to investigate the spatial pattern of earthquake occurrence. Based on nearest neighbor sequences, we could identify two areas. This area where small events occur but with high complexity, they are in, it is the area in blue here, whereas in this area we have the largest magnitude events, but the complexity is definitely a small one. Using closeness and out degree complexity index, we could find that this spatial pattern is confirmed, and that again the swarm-like sequences are standing along these the borders between the plain and the Friuli plain and the Julian Alps. However, when we analyze the clusters defined by stochastic method, though they are composed by essentially by the same earthquakes, still the internal structure is pretty different, and the spatial pattern is no longer observed. And we can see here in some detail how they look like, the different structure. You see that dominant events are still the same, but the structure is more complex. Again, here you have a dominant earthquake, but this, let's say, larger complexity is reflected by the different parameters, different index quantifying the complexity. Here you can see, for instance, a moderate size earthquake, magnitude 4.3, occurred in this area. You see that practically the two sequences are almost the same. And well, so there is an excellent agreement between the clusters identified by the two methods, and also the structure is pretty similar. But for the largest events, these differences increase. So the key points, the key elements we could get from this analysis is that we can investigate by using network methods taken from network analysis. We can get some centrality measures that permit to capture the features of the clusters. And whereas the identified clusters are pretty consistent with the two methods, just as we have seen for the nearest, for the background seismicity, still the stochastic declustering method provides a much more complicated internal structure. So I just come to some wrap-up conclusions, is just basically recalling that the nearest neighbor approach is pretty simple, with just 3 parameters necessary to apply the model. It's simple, data-driven, and effective method which can be applied to the cluster, the catalog, and study internal structure of sequences. It is clear that the stochastic declustering approach is more informative because it also assigns probability to each link between the events. But first, it requires a larger number of parameters and is therefore more sensitive to catalog completeness. And also, it seems to, let's say, that the complexity of the clusters is also reflecting the complexity in the model, so the multi-level triggering of seismicity. So for this reason, I think that nearest neighbor, it's more effective and more, let's say, objective in defining this cluster structure to be investigated for and correlated with physical properties of the crust, and to study evolution of seismic sequences. Just a quick example for recent small events in this area, which is the area of swarm-like sequences. This earthquake occurred in February 2018. Here you can see events with magnitude larger than 0.5 detected immediately after the event, and their connection. Here, the repopulated catalog, which was compiled afterward by increasing the completeness down to -1, magnitude -1, and still you can see that the method, the nearest neighbor, allows to connect to model the connection between events. And this is the graph structure that was obtained with the first data, and here is the complexity, here with the repopulated data, and you can see that even increasing the completeness of the data set, the structure is preserved, so even the lowest completeness permits to assess the features of the sequence. So the preliminary data permits already to identify the complexity of the cluster. And here, just to mention, if you wish to, let's say, to go deeper in this analysis, you can refer to these papers, which I will be happy to provide you. Thank you.
Thank you so much, Professor Antonella. It was an enlightening lecture, really educative for the young people and who are in this research in this particular topic, identifying clusterization and declusterization, and then identifying the complexity in the cluster. So wonderful lecture. Now I think there will be some questions or queries about this lecture. Yes, there comes one queries from Professor Karkalos. Yes, how many earthquakes did you take to estimate the B and D value for every cell?
This is a good question. This unified scaling law for earthquakes uses a telescope approach where you start from a large area, which is which can be, for instance, 2 degrees by 2 degrees, and then it zooms down to smallest areas of smaller size. And this guarantees that you have enough statistics to have the linearity of the distribution to assess the B and the parameters, I mean, all the parameters of the distribution. And also it accounts for rotation of the area so that it does not depend on the specific configuration of the area that you are considering.
Thank you so much. Do you also have some restriction on the number of earthquakes? Suppose you are taking 1 degree by 1 degree, and what will be the minimum number of earthquakes? Do you also restrict on the number of earthquakes?
Constraint is given by the linearity of the distribution at different scales. You fit the data only until the linearity is preserved. Then you stop. You discard the curves which are not linear.
Okay, thank you. Thank you so much. Is there any other questions?
I guess no more questions. We can wind up.
Okay. Then I think, yes, I think we can wind up. And thank you so much, Professor Antonella. It was a wonderful lecture. Now over to Pooja.
Yes, sir. Thank you. Thank you, Professor Antonella Pearson, for the interesting and productive lecture. Thank Dr. J.R. Kyle, sir, for chairing the session. So much, both of you.
It's my pleasure. Thank you. Thank you all. So I think we have we can call the day now. It is all over, or some more lectures are there.
All the participants. Yeah. And I also thank all the participants for their presence. Let us meet again tomorrow. And tomorrow's technical session will be 10 hours IST. Thank you.
Thank you.
Okay. Thank you so much. Thank you.
Thank you. So see you tomorrow.
Thank you.
Thank you. Thank you.